a scientist for 17 years. I started my bachelor's degree at University of Calgary in physics. And that was pretty cool because I got to build a lightsaber as my undergrad project. I can talk about that after if you guys want. And then I moved to Australia. And for anyone who's thinking about post-grad and things like that, getting out of your local town, local city, doesn't have to be a different country, but just getting out of your local city, I really highly recommend that. So I moved all the way to Australia because I had some family that was over there, and that wasn't so scary. And I studied for my my PhD in electrical engineering because sometimes they put quantum physicists in the electrical engineering department. Because even though we play with light and we think about quantum states, we then have to actually measure the light, right? And that's all electronics. That's detectors, that's filtering, that's digital processing, taking an analog signal, sampling it, and getting a digital output. That's all electrical engineering. So I'm actually very fortunate that I can play both sides of the coin, right? So a lot of physicists are lacking engineering skills and vice versa. And so it's nice to be well-rounded. Same with mathematics. You can be very well educated in a certain field of mathematics and then and very, very, not in another, but there's a lot of similarities in mathematics. So it helps you to be more rounded, not just as a person, but also in your scientific field. And then I moved to back to Canada, and I went to the University of Waterloo, and I became a postdoc at IQC. And I started there in 2015 and with Thomas Yonavine's group. And I'm still with Thomas Yonavine's group, and I'm now a research associate, and I'm also working with Thomas on the Keysat science team. So I'll be talking about Keysat. It's the Canadian Space Agency's quantum satellite mission that's going to be launching in 2 years. And my prof, Thomas Yanavine, he's at IQC. He's the PI for the science team. So we, as I said in my public lecture, we are like the NASA for Canada because we're the people in the room doing the mission control. Well, I mean, CSA are people in the mission control. We are helping we are helping support the mission objectives. And we're going to have like an operations center. We're building an operations center at IQC. Where we're going to be having, yes, because there's going to be a ground station. I will talk about all this. So I wanted to just go through the lecture I gave, my public lecture, but I wanted to give a slightly more technical side to it, right? So when I was speaking before, when I was going through these slides last week, if you saw, I was trying to speak to everyone, literally. So I wanted to just have like someone who's 10 years old, what is quantum physics? It's the physics of the tiny. It's the physics of the thing that when you stare at your hand and you stare at your skin, and if you could look even further, you could see a microscope, and you start to see the atomic structure. It's the study of the tiny. And I like this picture down here a lot because this is actually an electron microscope picture of chalk. And so if you just look at a piece of chalk, it's just white, and then if you zoom down, all of a sudden you get all these structures that we didn't see with our own eyes, right? And then I always like to show the Bohr model of the atom. I think Bohr was one of the greatest fundamental quantum physicists in the 1900s, because he was one of those scientists that could take all these different experimental results that didn't make any sense. For example, classical theory of an atom, it didn't. Classical theory of an atom didn't explain why an atom would still exist. In classical theory, in Newtonian physics, if you have an object that is constantly accelerating, either changing direction or changing the magnitude of your speed, though that's accelerating. And an object in acceleration will radiate energy. That is how classical physics works. So an electron in their world, they thought was circling the nucleus, right? Just like this picture. So if that's true, an electron is actually physically orbiting something. That means that its direction is constantly changing. And so then it should be accelerating. So then it should be losing energy. So then it should be spiraling into the nucleus, and we should not exist. I'm pretty sure I exist. So I'm pretty sure that there's something wrong with that theory, right? And so Niels Bohr took things like that. Also, black body radiation, right? the classical theory, the way the classical theory would explain how the electromagnetic spectrum, which I'm just going to show now because I'm going to talk about it, how the electromagnetic spectrum, how shorter wavelengths like gamma rays and X-rays, they're really short, right? And then radio waves are super long. And so they thought, hey, if it's really short wavelengths, then you can fit more energy, you can fit those shorter wavelengths into that spectrum, more of them, right? So you could, the way that they thought about, the classical physics thought about a fireplace, like a fire, that it should be, it generates heat, right? But then it should be also generating tons of other radiation too. So we should be bursting into flames or baking ourselves with UV sitting in front of a fireplace, in front of a fire. Well, that doesn't happen because there's that black body curve, right? It doesn't go off into infinity. It doesn't continue having lots of energy in the higher frequencies. It has that shape just around the infrared and then like a star spectrum. Anywho, so these were signs that something was wrong with the way that we were thinking about physics in the early 1900s. And Niels Bohr is one of the scientists who came up with the theory of, hey, what if the electron could just stay in an orbital and it could just chill there and it doesn't have to worry about moving and accelerating and stuff like that. It's just there. It's in a stable orbital. And that's what these shells are, which some of you might have already seen. So that's what quantum physics is, right? It's a study of the tiny. It's a study of things that, you know, if you throw a bowling ball, if you can throw a bowling ball, that's classical physics, right? So now what is light? Well, light is, as I said before, an electromagnetic wave. So it's energy. It's a field. It has an electric field and a magnetic field, as shown in this picture, that are perpendicular to each other. And that is perpendicular to its direction of propagation. And I'm going to talk about polarization. Polarization is just a way that we label light. So the direction of polarization is determined by the direction of the electric field. That's just a nomenclature. We had to choose one, and it kind of just made sense, I guess, at the time. Electric field, polarization, sure. It probably was easier to measure the electric field than the magnetic field. Anywho, so... And then we have here, I like to show the approximate scale for the different wavelengths of light. So, you know, we have radio waves all the way up to gamma rays, right? And then visible light, the rainbow that we actually see, it's a very tiny fraction of what energy is out there. And radio waves are on the scale of a big building, right? Because that's how radio waves can travel over long distances across the Earth. But if you start to get into really, you know, tall mountains, high rises, stuff like that, those objects block it, right? But if you had just, you know, the plains of Saskatchewan, you could send that radio wave as long as you want. And then on other things, I mean, I don't want to go too much through that. The other thing I wanted to just point out on here, because I know we started a bit late, is the wave-particle duality of light. So I'm going to talk about a photon. A photon is a word that we use to describe a packet of energy, a particle of light, an indivisible unit of energy. And you can think of it like a marble. It's pretty hard to break up a marble, right? Like if you really want to try, you could. But a marble is a marble is a marble. So a photon is a photon is a photon. And you can think of it as an individual entity because it's a lot easier visually when we're talking about sending light, sending information using light. But as we know, light also acts like light also acts like waves. And so in this picture, I'm showing the young double slit experiment. So you have your light source, and if you think about it, almost like lapping against the side of a wall, like an ocean wall, and then you just had these two little holes, and then some of the water was allowed to leak through, right? You get these bands of interference and you know, destructive interference where the wave cancels out, and constructive interference where it'll add up. And just as you see on the ocean when two waves crash into each other and they muddle into nothing or they go into a big wave, that is interference. And so this experiment is one of the first experiments that showed the wave nature of light. And what's really cool is they've repeated these experiments, as you probably know, where you monitor a little, you put something, a detector or something in this little gap, right? And instead of just letting the light go through and just be whatever, you try to watch what it's doing, right? And you try to watch each individual photon. And if you change the way that you view this experiment, you actually destroy the intensity pattern. So if you watch, you destroy the intensity pattern, you just get two big dots where the light came through the hole because you watched it. You made the measurement. You made the measurement and you collapse the state. That is what quantum physics is. Okay. I don't want to go too far into that. Do we have any questions right now? Because no, I haven't talked about anything of substance. So what is what is QKD? So quantum key distribution, that's what QEYSSat, that's one of the main the satellite QEYSSat has two fundamental reasons to exist, right? One is security and one is fundamental science. But the security aspect is the one that I chose to talk about in this talk. I might give another one about the science aspect, because as soon as you start to combine a satellite, which goes really fast, with quantum physics and entanglement, which is quantum physics, we start to play around with that realm of general relativity and quantum physics, and does this make sense? And so like detectors and accelerating frames, because if we have detectors we have detectors on the satellite, our receiver is on the satellite, so that satellite is going through an accelerated frame relative to the ground. This is where cool physics is that we couldn't do on the ground. So that's the motivation behind QEYSSat. Okay, so why do we need QKD though? So the point is that the security of quantum key distribution, which is a way to generate an encryption code, an encryption key between two people, two parties. So it's that key, the ability to crack that key, it's not based on the computational hardness of solving mathematical problems. So the current public key encryption that we use now for banking and all that kind of things over the internet, it's usually based on factorizing very large numbers, because that's hard for a computer to do, a classical computer to do. But a quantum computer has other abilities, like factorizing large numbers becomes a fairly easy thing to do using Shor's algorithm. And I didn't go into Shor's algorithm for a reason, because that's not the point. But if you want to know about it, I can tell you. So anyways, the QKD part of it, it's actually based on the physical process of how we generate the key. And so once that key has been securely generated, it's not vulnerable to any further future attacks or from an attack from a quantum computer. So an encryption key that's generated by a QKD protocol is secure today, and if it's secure today, then it will remain secure even as powers advance. And this is known as forward security. That's a term that if you get into cryptography, post-quantum cryptography, quantum cryptography, any kind of cryptography, you'll start to learn these terms. And so I said before, right, a photon is a particle of light that can carry a unit of information. So a quantum bit, and then we short it form to qubit. And this is very, very, very important. Quantum information can be transferred, but never copied, never cloned. And a measurement always disturbs the state of the system. And the metaphor I used last time about the measurement disturbing the system, right? If you imagine just like some water, like in a bath, and you just use your hand is your measurement, right? And the bath is a state. And so if you slap the water, you've disturbed the water, right? The water reacts and it starts to move, right? Your hand is the measurement. You've disturbed the state, the water. So anytime someone tries to measure something, they disturb the system. Whether it's the good guys, right? Alice and Bob, who need to do a measurement to do this, to do the protocol, or if it's a bad guy, like the eavesdropper Eve. So, and then the never copy part, that's the no cloning theorem. And that's the, if we ever wanted to make a teleporter, we would be having to destroy the person in one location and completely recreate their quantum self in the other location, because you cannot have two Kataynas. I would love two Kataynas. No, it would be too much. But you can't clone in quantum physics. And I can show you not in these slides, but I can show you if you ever wanted why there's no cloning theorem. It's very easy to understand. Okay, so now I wanted to give you an actual physical example of some work that our group did and that I did at IQC that was on QKD. So we had a grant with the U.S. Navy, and say they have two ships that want to communicate securely in the ocean, and you can use quantum key distribution and light, right, to transmit a laser from Alice on one ship, who wants to communicate with Bob, and they just want to generate the encryption key. They're not sending the message right now. They just want to generate a key. And I will explain what that means in a sec. All right, so then they use photons, and this picture here. This is a false picture of false color picture of what a beam of light looks like if it has a Gaussian shape. So like very nice, the most efficient beam shape, like a collimated beam to send in free space. And it basically looks like a bell curve, right? If you took a slice through this, it looks like a bell curve. So that's a Gaussian beam, and this intensity scale is just showing brightness. So dark is 0, 1 is bright, so red is bright, and it's just to show that the center is bright, and then the light dims towards the sides. And then because of reality, if you send light through atmosphere, especially if it's over the ocean, especially if it's say a 1 kilometer horizontal channel over the ocean, that is literally the worst possible turbulence that you could do, because the ocean is just one giant heat mass, right? So the air above the ocean is always circulating, it's always getting warmed, cooled, moving. And so that's turbulence is when light travels through moving air. The changing index of refraction of the air changes the phase of the light. I hope I didn't lose anyone just there. So the change, so if you want, so yeah, the index of refraction of the air changing affects the phase and amplitude of light. And so like you can see this, you'd be familiar with this, right? If you look at stars, if you see stars that are straight up above your head, it's very clear night, they're not really twinkling too much, right? They're just kind of there. But then if you see, for example, Mars or Venus or something like that, very, very bright planet or star that's low on the horizon, and it's twinkling a lot and it's moving a lot, and it almost looks like a plane that's, you know, it's sometimes not if it is a plane. Anyways, that twinkling, that extra twinkling, is because you're looking through a thicker layer of atmosphere. You're looking through a lot more air when you're going through a horizontal channel. We see this too when we talk with the satellite. When it's straight overhead and zenith, we have a different turbulence, different everything, right? Compared to when it's going low on the horizon. So this picture here is actually a simulation of what light looks like after it's gone through 1 kilometer of turbulence at sea level. And so the nice Gaussian beam basically just breaks up, and this is just one snapshot, so it's always moving. So if you have, like, there's videos of the Canary Islands when they did the free space experiments for QKD between the two islands. It was about 1 kilometer free space link, and they have a video of the beam on the wall that was coming from the other, like the beacon or whatever, and it's just moving. It's just this spectral, crazy pattern moving, right? Okay, so I said how a person in the system disturbs the system, right? So if a hacker, for example, Eve, and because we're in the ocean, so it's Ursula from The Little Mermaid. So Eve is sending her own laser beam, and say she's trying to manipulate Bob's receiver. So the beautiful thing about QKD, and I'll show you why, is that a hacker can be detected in the channel because her measurement is disturbing the system. Okay. And just to give you know, a quick little zoom back to why we're talking about this, you know, because this is originally quantum plus space. This figure, it's from a couple years ago, but it has a lot of the major countries and missions that are currently going on in the quantum space race. So every single one of these satellites has a QKD source or receiver. The direction, I'll go through this picture more in detail in a bit, but the direction of the beam shows you if it's an uplink or a downlink. So KeySat is an uplink. Our ground stations are on the Earth, and our receiver is on the satellite. And you actually can see in this image 2 of the QKD missions that we've done. So Thomas Yandevine's group, they put a QKD receiver in a plane, and they flew that. Well, they didn't fly it. The NRC flew it. They flew the plane and then linked with the ground and proved the concept was viable, which led to KeySat being officially funded and launched and begun. Anywho, so if we go back to QKD, are there any questions before I go through this protocol? We go with no. Okay, so one of the basic quantum key distribution protocols we have is called BB84. So it's named after Charles Bennett and Gilles Broussard from University of Montreal. So Bennett's from IBM, and Broussard is still at University of Montreal. And what I'd like to do now is step through the BB84 protocol, because this is the protocol that we are going to be doing. Well, not this protocol, but it's hard to be technically correct, but also not confusing. We do BB84 for QKD for the KeySat mission, but we do a slightly modified version of BB84 because this was made in 1984, and people have made we have progressed the protocols. We have figured out better ways to reduce the errors and make QKD work even over very long distances because you have lots of loss. So there's something called decoy state. I'm not going to talk about it, but we actually do decoy state BB84. Okay, but the BB84 is the basic thing. So as I said before, if we wanna generate this code between the sender Alice and the receiver Bob, and we want to use these individual particles of light called photons, we basically want to make an alphabet using light. And so I liked this analogy before. If you were a kid in school and you wanted to write a note and you didn't want your teacher to read it, sometimes you could figure out like a code. And so, you know, A becomes H and B becomes G and C becomes J and D becomes I and blah, blah, blah. This is your alphabet. This is your cryptography. This is your code. And then you use that code to write your message. Okay, this is not the message that we're sending right now. This is just the code that you then XOR, which I will explain. Okay, so there. So we want to talk about the alphabet, and it's a lot easier when you talk about an alphabet instead of talking in language to talk in mathematics. It's still a language, and bits is the binary language. That's the most fundamental language. So the way QKD is you assign bit numbers, right, 1 or 0, to different polarization states. And that's how you build up a string of zeros and ones that's random between Alice and Bob. It's random, but it's shared. And its randomness guarantees the security. That is true. Okay, and then I talked about this before. We're going to take the polarization label. So with light, you can use any you can use different labels, right? You can use color, you can use polarization, you can use phase to do different protocols. And so, but the most fundamental one and the first protocol, the way it was originally proposed, was using polarization. And so we assign. We also need, so we need 2 non-orthogonal bases. So non-orthogonal meaning you have what they're calling rectilinear. So HV. So HV. So horizontal and vertical, they are orthogonal, right? Diagonal and antidiagonal, they are orthogonal. That's 45 and minus 45. And then, but then HV is not orthogonal to DA, right? Because they're at 45 degrees, not 90. We want two bases that are non-orthogonal for this protocol, because that's how the math works. So then what Alice does is Alice chooses which state to send. So Alice chooses to send H, B, D, or A. It's a randomly chosen state. The randomness is incredibly important. If there was a pattern in what she is sending to Bob, that is a pattern that can be exploited by any hacker. That is just how cryptography works. Like even now, when they're generating these kind of codes, if you can hear a pattern in the noise in the signal, then you can crack it. And then Bob chooses what basis, what HVDA, those are the bases to measure in. So again, this is a random decision. And here we're showing the actual optics, right? So with light, when you want to measure the light's polarization, we use something called a polarizing beam splitter. And a polarizing beam splitter cube, it'll basically, ironically, the way that they've drawn this is not the way that it's usually drawn. Anywho, so usually vertical is reflected. This is the convention. I just noticed this now. My apologies. and transmitted is horizontal. But you know, whatever. You can have it either way. The point is that this piece of glass has the ability to direct one polarization in one direction and the orthogonal polarization in the opposite direction. And so with this thing here, this rotator, that's actually a half wave plate. And so the half wave plate takes a, depending on what angle, it's a birefringent glass. And so depending on what angle the wave plate is at relative to the polarization angle, what angle of the, it's called the fast axis and the slow axis of the birefringent glass. Depending on what angle that is relative to the polarization will dictate how much the polarization gets rotated by that birefringent glass. So you can rotate horizontal light to diagonal light by having a half wave plate at, I think it's 22.5 degrees, but I'm very tired. So the point is you want to measure HV and DA and you use polarization beam splitter cubes and also a wave plate to isolate the different polarizations. So this is the actual way to implement it. So, and we have a QCD demonstrator, like Thomas, as part of an outreach thing, we actually put together a demo, and it implements BB84, and it does this with polarization. So I'm gonna walk us through one of the protocols, right? Like some of these steps here, and so we can build up some statistics, okay? So say Alice sends, you know, a diagonal photon, but Bob measures in the wrong basis. Bob measures actually in the HV basis. And because of the randomness of the measurement, a photon that is diagonally polarized when it hits this PBS. So if it was if it was a diagonally polarized at 45 degrees, there's no rotator here, right? So a 45-degree photon, when it hits that PBS, it has a 50-50 chance of either going vertical or horizontal because it's a 45-degree polarization photon. So it's literally made up of half horizontal light and half vertical light. But it's a photon. It can't separate itself. It can't send half of itself to one detector and half of itself to the other. It's a photon. It's an indivisible particle of light. So it has to make a choice. It has to make a choice, and it's a flip. It's a flip a coin. And if this polarizer is perfect, and if the photon is perfectly 45 degrees polarized, it's a perfect 50-50 chance. So if Bob measures in the wrong basis, he has a perfect 50-50 chance of either getting the right answer or getting the wrong answer. So in this case, Alice had sent a 0, and Bob measured a 1 in his measurement system, okay? So that's wrong. That's an error. So this part here, the public discussion, it's to find these cases, okay? So Alice and Bob, after they've already generated all these things, they announce a few of these cases to figure out when they were, when the basis was linked up and when it wasn't. Because when the basis was not correct, you have to throw that out and start again. Okay, so now let's try another one. So now Alice tries antidiagonal, so it's a 1. This time Bob measures in the proper basis. Now, if Bob measures in the proper basis and there's no, issues with the randomness or anything, he will get the correct answer. So they keep that bit. And now they see down here, it says Alice and Bob's shared sifted key. So they have a bit now. And then they just keep doing that, and they just keep building up all the bits, right? So Alice will keep sending different photons. Alice and Bob will keep measuring. And then when Bob chooses, because the randomness is important, so it has to continue to be random, okay? As Bob measures in the correct basis, they get to keep that bit. And it matches, okay? Now, but what about Eve? Because if Eve was in the channel, she'd be making those mistakes too. If she tried to take a photon away, measure it, and then give back to Bob, she's disturbed the system. And she can't know with certainty what Alice, what basis Alice had sent in. She doesn't know that. She doesn't have access to that information. All she has access to is, give me one of these photons. And so if Eve is literally hacking Bob, right, back in the ocean, and if Eve is somehow able to disturb Bob, if Eve is able to what I call couple, right, what we call couple her measurement to the system, then she could learn information. So there's a trade-off. There's a physical implementation side, right? There's a theoretical 100% secure. Theoretically, if you do this protocol, there's no pattern, there's randomness, everything's fine. Physically, there's no such thing as a physically perfect beam splitter. There's no such thing as perfect randomness when you're physically generating it, right? One of the best random number generators that we can make is literally sending a single photon to a 50-50 beam splitter, because that single photon has a 50-50 chance, a perfect chance, right, of going either way. But it depends on your ability to generate single photons. If you do not have a genuine single photon emitter, then you could have 2 photon events. If you have 2 photon events, Eve could take one of those photons away and you would never know. So that's actually one of the hacks. So avoiding multi-photon events is very important. And remember I said decoy state? Decoy state is a way to play around with the intensities that Alice sends, so that sometimes there could be more than one photon, but sometimes there's less than one photon. And by playing around with that, you can improve your key rates for higher loss cases. So as I said before, you have Keysight here and the plane mission. So I just wanted to show you some pictures. So in Waterloo, at IQC, Thomas Janevine, he started this group like 2011, and they began all kinds of fundamental tests to lead up to this QEYSSat mission. His dream has been to do the QEYSSat mission, right? So one of the first things that you had to do was mount, or not you, they, was mount their receivers. See these yellow, orange fibers? That's the multimode fibers connected to the detectors. That's the, HVDA. Actually, that is correct. These are the HV. That's why they're exactly horizontal vertical. And DA, it's actually rotated, because that's the easiest way. Instead of having a wave plate in the way, you just literally just rotate your bases. You rotate your detectors, because that polarization, right? So they mounted this receiver in the back of a pickup truck. And then in Waterloo, there's a rack. I can't remember what rack stands for. I've been to campus in a year. All right, so RAC is on campus over by the Quantum Nano Center, right? And the truck was driven along one of the roads in Waterloo. It's a 1 kilometer link between the roof at RAC and this truck. And they did it. This was before I joined the group. And then they took this giant receiver, that proof of principle demonstration that worked, right? And they miniaturized it into this tiny little thing here. This right here, this is that. Pretty cool. And then in the next stage, so you demonstrated with a truck, fantastic. Now, that's going kind of slow though. What about a plane? Because the angular speed of a satellite is very fast. So you need to check, can we track, yes. So this is a 10-second exposure right here. And that streak, that's actually the plane, this plane. When NRC were flying it over and we were doing a link. And this is the ground station at Smith Falls. And that's Thomas right there. And you can see behind him, that's the receiver. And they flew this plane with the door open. And a couple of our colleagues were in there, strapped in. Didn't want them to fall out. Yes. And that's all I want to show. Okay. So then from the plane, because we successfully demonstrated this QKD link between a ground station transmitter in Smith Falls to the receiver payload on this NRC Twin Otter plane. So that demonstrated the viability of the Keysat mission. And so then shortly after that, the Canadian Space Agency and the Canadian government announced funding for Keysat. And then named Thomas, as I mentioned, the Keysat science team principal investigator. And so I'm helping with both the research side and also the what's called coordination side, because we have a Canadian science team for the Keysat mission and also an international science team. And what does this mean? So there are researchers all across Canada at all these different universities who want to contribute in some way to Keysat. So maybe they have a detector that they want to contribute to a ground station. Maybe they have an entangled source that they want to use to send a different type of light. Maybe they have an atomic memory and they want to link an atomic memory to Keysat, right? These are all things that these are all one group cannot do everything. That one expert, right, is never an expert in everything. So we are experts in IQC. Thomas, he's an expert in QKD, an expert in satellite stuff. We have quantum dot. We're working with Michael Reimer, also at IQC, quantum dots. Now, out in Calgary, for example, and in Edmonton, out here we're doing atomic memories and quantum repeaters using atomic frequency combs, like completely different science that will add to the mission. So my job with Thomas and a few others is to help coordinate what the researchers want to do, what experiments they can do, what the CSA is comfortable with. CSA has to sign off on everything. It's their satellite. We are just helping. And then making sure that you know, it happens. It's like if someone wants to link up an atomic memory to Keysat, we got to make sure that the atomic memory is ready to go. It's in the right place. You know, there's a lot of things to lead up to it. So I actually led, this is me up here, I actually led a virtual kickoff meeting just last month of the science team. So this is the current Canadian science team. And on the call, we had like 30 PIs, principal investigators. And somehow we got through like 20 presentations in just an hour and a bit. And it was very good. Virtual meetings. So yeah, I just wanted to show this again and say that this picture has a lot of detail in it, and they use the direction of like the narrow pink and the narrow end of the pink path shows the QKD source, and the broader end shows receiver. So in some of these missions, for example, the Chinese missions like Nicias, It's a downlink. So they have their QKD source on the satellite, and then they put the receivers on the ground. And there's advantages and disadvantages to doing uplink versus downlink. A major advantage of doing an uplink is that you can do any kinds of sources on the ground, and you just have to make sure that they are in the right pass band, the receiver band, right, for your receiver. So we're going to be receiving light between 780 and 795 nanometers. So as long as whatever we send up, whatever photon, whether those photons came from a quantum dot, from a nonlinear crystal entangled source, from an atomic memory, it doesn't matter. As long as it's in that wavelength, the receiver will receive it. So having a quantum uplink channel and having our quantum receiver on the satellite, this gives us this ability of having multiple quantum sources on the ground. So we can also test various ground to space links. And so like linking fiber networks, atomic memories, as I said. And so one of the demonstrations we're going to be doing is this quantum links and space QKD. So we're going to have ground stations, a few ground stations in Canada, and then also around the world. And in the first year, it's Canadian focused. And we're actually making a transmitter telescope that's compact and portable. So like IQC, Thomas's group, we're making a quantum ground station. And like you saw that trailer, right? It's literally portable. So we can just take it outside of the city and link up to the satellite. And we're scouting for ground station locations now. That's one of my jobs. So yeah, the reason for QEYSSat, right? The quantum encryption and science satellite is the study of quantum links, also entanglement and relativistic settings. This is new science that you cannot do on the ground. And we're hoping to launch in late 2022. Cool. Well, thank you. And this is the QKD demonstrator that I was mentioning. So in this box we have Alice. In this box we have Bob. This alarm is actually to signify when Eve, which is this red little box here, we made an Eve, so someone could actually, you know, turn up the dial and start manipulating with the light. And then if they manipulate with the light too much, the alarm goes off and the computer says, "Ah, eavesdropper, stop." And then you see there's these buttons. See, I built this, so I know exactly what this is. I know this picture is small, and I apologize. But if you want to see it in real life, when we're allowed to see things in real life again, we have this. And we're making another one, and it's going to be remotely activated. So physically, you would push one of these buttons, HVDA, and this is to send the light. And then over here, you push one of these buttons, HV or DA, to measure the light for Bob. And so we're making another one of these demonstrators to have it work remotely. And so we just have the boxes set up like there's motors that like manually move the wave plates to change the polarization states. And so the computer will be linked up to the internet. And so someone can log in and just be like, oh, I want to generate some code, some keys, and then they can just operate it. And if you wanted to take a look, IQC, you know, we do a lot of outreach, and so we did a video about this, and yeah, you can find that. And I think that's it. Thank you. 7 minutes for questions.
I have a question.
Please.
So that proton hack where some of the information is stolen as it's being transmitted to the satellite, how effective is that hack at recovering information? Like, how bad can it get if you're not careful?
So if a hacker was trying to hack the satellite, for example, we would start to get error messages that would signify that something is wrong. Because before you launch satellites, before you do any kind of things, you have your Alice and Bob. You have to characterize your system. So as soon as you launch it into the real world, you already know what to expect. And so really the security behind all this is the fact that when someone tries to manipulate the state, they are going to cause an error. Like they can't do it perfectly every time, and they can't clone the light and then send you a clone. So the problem with the yeah, no, I went off on a different tangent, but did I ask? No, I didn't answer all of your question. What's the other part of your question? I only answered part of it.
It was how bad can it get if you're
Yes,
not
how bad can it
careful?
get? There's an error rate. It's literally there's an error rate, and if it goes over 8%, the protocol's done. So there's like a certain amount of error that you can tolerate by using privacy application and like classical cryptography ways to just grow a key from a seed. That's safe. But if the errors are too big, then the protocol fails.
Okay.
But then people came up with like decoy state, for example, and so decoy state, because of it's almost like building in a redundance into the states that Alice is sending, and so you can tolerate a much higher errors. So okay, have you heard of dB, like decibels?
Yeah.
Like the units, yeah. So if
Yeah.
if I say a quantum channel has 90 dB loss, 90 dB loss. That's tons of loss, right? Compared to like 10 dB of loss. Okay, so 10 dB of loss is like small. 90 dB of loss is huge. Okay, we're good. Okay, so there's different protocols. There's different ways that you can do QKD. There's one that's called continuous variable QKD. It uses light, and instead of using polarization, it uses phase and amplitude of light. So, and it uses a different kind of detector. Instead of a marble detector, instead of a single photon detector, continuous variable uses home running detectors. And so it's all still light, but it's looking at it differently. And so why am I saying this? We're doing discrete variable, we're doing marbles, we're doing polarization, we're doing individual single photon detectors, because that kind of a protocol can handle things like 90 dB of loss, which is huge. CV, continuous variable, it can only handle 10 dB of loss. You literally cannot do that version of QKD in a satellite link, because the loss to the satellite is between like 50 to 60 dB of loss, just the satellite, just from the atmosphere and light spreading, and
Okay.
So why am I saying this? We came up with other protocols, right? Like the decoy state. It's like it has a higher tolerance for loss. You can still generate a secure key even with like 90 dB of loss. Whereas there's other protocols that they have different advantages, but then they can't handle as much loss. Yeah.
Okay.
Yeah. By the way, Norbert Lukenhaus. He's a lecturer at IQC, and he has some public lectures on YouTube about QKD and about protocols. I really enjoy the way that he explains things, because he's a theoretical quantum physicist, right? So he approaches it from the mathematical protocol side, but he is very very well established in the physical implementation. Like, we work with him a lot on, okay, so this is your protocol, but then this is how we're going to do it in the lab. So then how do we link the math to the lab, right? And so Norbert's very good at that. So if you wanted to know more about this, I'd look up his lectures on YouTube.
Okay.
Are there any other questions?
What was there about
Yeah,
making a lightsaber? Oh, you know what? Let him go ahead.
Yeah, you mentioned that there's fundamental science applications as well. We can like do quantum in relativistic settings. So I was wondering if you could elaborate a bit about that, and what new things will this technology allow us to explore that we could not before.
Yeah. I mean, I don't have specific examples ready for you right now. There is a paper that Thomas is on, published in 2012, where they talk about like if you reach. Oh wait, I have a slide. Hang on. No, I have a slide. Yes, thank you. this paper. It's also on the archive. Like if you just search this title, and yeah, so this is one aspect of why we want to launch satellites. If you start to move at faster speeds, okay, that's what the scale is. This is speed here, and then it's showing. So when we're doing ground-based experiments, right, the length scales that we're dealing with, and the speeds that we're dealing with, they're not interesting, right? Like the Large Hadron Collider, they had to push that to such a high energy level to finally get something interesting, right? You had to really push to the extreme. So when we're doing experiments in quantum physics, and my light just has to go, you know, a few kilometers around the table or around some fiber or whatever, that's not a length scale that's like a you know, planets scale, right? So by launching a LEO satellite, okay, you start to get faster for sure. And so that relativistic speed, I think that there's some, I believe, I need to check, that there are some predictions that, you know, for dark matter, dark energy, I think it's dark matter, there's some predictions that if one of the quantum gravity theories is correct, then an accelerating detector is going to have a certain kind of like redshift or blue shift, like it's going to do something. An accelerating detector, a quantum accelerating detector, is going to do something, and I don't know what that something is, and I apologize, but it's going to do something. And one theory says it will do this, and the other theory says it will do this. And if we have that answer, if we have that ability to do that test, we could actually start to have evidence of what quantum gravity theories have legs, right? And then a geosatellite. So a geosatellite, a geostationary satellite, they're higher up, and they're stationary, so they go slower. But again, you get more distance. And then the really cool thing is going to be like lunar tests. So like Thomas, my prof, he's on the science team for the JPL mission for the Deep Space Quantum Link. So if you want to know about quantum physics and general relativity experiments, look up Deep Space Quantum Link. It's a project with NASA JPL. It's going to launch soon. They're doing the science team stuff right now. So next couple of years. Yeah, I think it's mainly just like testing long range entanglement is the thing that you get to do. So like we understand if we do an entanglement measurement in the lab, right? Bell state measurement, like it makes sense. But then what if that photon is so farther away? The light cone. Do you know about the light cone? Have you heard that term? What grade are you in? What year? Yeah.
Yes, yeah, I'm familiar with light cones.
Yeah. So in special relativity, when they want to draw like a 4-dimensional picture on a 2-dimensional graph, they draw, you know, space and time, and then there's like a light cone, and then whatever, I can't remember the diagram. So there's a line, and if you're faster than the line, then that means you're superluminal communication, right? So so when you start to get these longer length scales, then basically your photon source is like you literally test whether you are communicating at the speed of light or faster than the speed of light. Like, is entanglement actually instantaneous, or are we just not pushing the length scale, pushing it enough, right? Does this make sense?
Yes, no, that was a really great answer. I really enjoyed that, and thanks for the reference as well. I'll have a look.
Good. You're very welcome. But yeah, that's it. Like if we had an entangled source on the Earth, and we kept one photon on the Earth, and we send one to the moon, right? and then we do a Bell state measurement between the Earth and the moon. Like, that's a Bell state measurement between the Earth and the moon. And it's supposed to be quantum physics. Like, it's not supposed to work. I mean, it's supposed to work. Is it gonna work? I don't know. Like, that's literally, we've never done that before. This is the next session. Like, this is like when they made the Large Hadron Collider. Like, they never made energy that powerful before, right? They didn't know what was gonna happen. We had an idea. Yeah. Next question. I think
no one else has anything.
Yeah,
then I want to hear the lightsaber story.
I should pull up that picture. No, if you give me a minute and I'll pull up the picture.
Sure.
This picture is so much better. I think one person had another question.
Yes. Yeah, I heard someone else chime in as well.
Go ahead while I'm finding it.
Yeah, I was asking that, like, you were saying that your role in the project is concerned with, like, I guess, making the collaboration happen and, like, seeing how the different research groups interact with each other to make this very big project. And I guess, like, at least, like, when I think of it, like, it's a different skill set from technical physics, either theoretical work or experimental. So what do you think about that? Like, like, how did you go about developing that, and yeah, how did you get good at it?
Yeah, exactly. Yeah, no, you're 100% correct. So, like, when I was a postdoc with Thomas in 2015 till basically 2019, I was doing the research side, right? So I was in the lab and doing experiments and helping supervise students and, you know, grant proposals, things like that. And then when the Keysat mission was announced and when Thomas was named the PI, they looked to me for some help with the organization and the coordination side, because I understand the science, and I'm a good communicator, and I'm very organized, and I'm literally keeping track of hundreds of people, and I'm okay with that. There's a lot of people not okay with that. I have a spreadsheet that is like beautiful. It's like, this is my bread and butter. So I'm very, 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 very fortunate that I'm able to find a job right now that pays me, that combines my passion for physics and my skill sets of organization, communication, and just being a kick-ass scientist. So I'm still working on the research side as well as doing the coordination side. So I'm helping with, like, modeling for the link analysis. So this stuff, the beam here, if I go back, this stuff. This is actually stuff that I did, right? So I was generating these holograms using MATLAB, and then each of these holograms, each of these black and white scale pictures, it's a different strength of emulating turbulence. And then you can see, anyways, this is just something I did. So the point is that, how did I get into this? I'm literally the one person in the world that can do this job. Like, not to sound too, like, full of myself, but it's true. Not many people are good at talking. Anyway, let me stop sharing this one and show you the show you this. Now, how do I show you this? This one. Okay. No, just go big. Big. Yes. Cool. You see that?
Yep.
Yep.
All right, cool. So this is the this is a lab at University of Calgary. This is my undergrad project. This black box here is a 1 watt green laser coming out, okay, hitting a mirror, going through a lens, expanding because we wanted it to be a bigger beam. So this is now a collimated beam of a larger lens. The reason you can see the light in the air is because I was not allowed in lab when my prof at the time and his postdoc did this. Russian guy, amazing, awesome scientist. They were smoking in the room to get free space particles. You're not allowed to do this anymore. Free space particles in the air so that you could actually see the beam. And I wasn't allowed in because it's a 1 watt laser and I was an undergrad student and they didn't want me to die. I agree. And that glowing thing there, that is a polarizing beam splitter cube. That thing right there, that has a piece of glass in it. It lets light transmit or reflect based on its polarization, just as I said before, right? And then behind this shiny thing, there's a conical mirror. So a cone-shaped mirror, okay? And then, if I zoom in a little bit more and not break the system, no, I can't. Okay, you see this super thin, really thin beam that's the same size and same intensity, and then all of a sudden over here, it just diffracts away. It just goes away like tails, like disappearing, right? That is the lightsaber. That's a Bessel beam. That's a almost 1 meter long free space optical beam, okay? And it's called a non-diffracting beam because what happens is the light hits the cone, okay? And it hits the cone, and as the light hits the sides of the mirror, of the conical mirror, they interfere. So they interfere, they interfere, they interfere, they interfere. If I had an infinitely long conical mirror, I could make an infinitely long lightsaber. I had a finite mirror, so we have a finite lightsaber. And then once you hit the end of the conical mirror, there's no more interference, right? There's no more mirror to cause the light to bend, to interfere. And so you just get this diffraction part. What do you think?
I think that's cool. I like that. And it's
And
like, I
we
can
got
understand. Sorry, no, I was going to say, I can understand why smoking is no longer allowed in the lab, but it is cool seeing all of the laser effects.
Yes, and now we have safer ways. Like there's like an aerosol spray, you know, that you can use. I think
Right.
Thorlab sells it. Yeah.
Oh, okay.
Because you need to take pretty pictures, right? You know, it's part of our job is to communicate. It's not just to do the science. Like it's also to communicate. Like what's the point of it's like if you were a composer and you made all this amazing music and then you're the only person who ever got to listen to it. Well, that's great. It's a little selfish too.
Yeah. No, I helped out in the laser lab for a bit, and I was a little sad seeing all the experiments and that you couldn't see the laser going anywhere except at the end. You just see a bunch of mirrors lined up. So
That's right.
yeah, it's fun
Right.
seeing them.
Yeah. I love the laser that's my favorite color is purple, and there's a laser that's like 455, and it's just that beautiful like blue purple, and your eye can't really, it's not very sensitive to it. Like green, you're super sensitive to green. Like if you see a green laser, you're like, oh shit, even if it's only like 1 milliwatt, you will instantly react. Because your eyes, your rods are more sensitive to green, but to this blue purple, your eye is like, what's going on? And then on the mirror, it makes this beautiful speckle pattern that looks like a fractal pad, like a flower. It's so pretty. I miss that. I miss the lab. Anyways, I'm happy to answer if you have any more questions or anyone. Thank you for your patience getting me sorted out. Sorry for the delay.
Oh, no worries. We've had that. Just about every speaker had to have a little bit of tinkering before coming in. I think
Yeah.
that's just the way of online seminars, really. Thank you for agreeing to come in.
Well, thank you. I'll stop sharing and yeah. Okay.
And someone just posted in chat thanking you for coming.
Ah, thank you very much, Julia. I appreciate it. Yeah, well, if anytime I can talk with people, you know, it's yes, I appreciate it. Thank you. And reach out, anybody. You can find me on the internet, obviously. And my email, k2kuntz@uwaterloo.ca. That should be on the IQC website. We're always looking for students who want to help out, you know, like for undergrad projects or future grad projects. You know, like Thomas's group is always evolving and changing, and we have a great group of people right now. It's pretty awesome. So yeah, just thank you.